Let's have our
Zico, when are you publishing?
What was this?
When are you publishing?
This, yeah, I'll mention.
so I'm trying to figure out the way to say, let's have our last talk for the ethics session. But of course, Zico is going to follow the highest ethical standards. So his particular ethics talk will be on, not on verification, will be on an architecture.
A new way of looking at depth in networks. Okay. All right, so thanks for inviting me here, Matisse. And actually, I've changed the topic of this talk a little bit from what's in the schedule. I did not get the change in topic in on time, but it's actually quite related to what I was talking about before. But in preparing the talk, we actually have some new work in this area, and so I wanted to kind of focus on the particular new way of viewing depth in deep networks. And so this model we've been working on, and this is largely work with my student Xiaoji Bai, as well as Vladlen Kolter from Intel. The model we're working on is called deep equilibrium models. And because it's a common trope in machine learning these days to have this kind of title, the subtext here is one implicit layer is all you need. But of course, because that is all you need is also very overused, I have to sort of clarify that and say, no, really, we actually have proven everything. This is actually all you need. Which seems weird, right? We don't think about one layer being sufficient to do much in deep learning, hence the name deep learning. So I want to talk about, it's not actually maybe that deep a statement, no pun intended, but I want to talk about what I mean by that and what this model is actually really doing and how I think we should be thinking about depth differently when it comes to deep learning. So okay, let's start with the story we all tell. This maybe is not working. Start with the story we all tell about depth, which is that when you have a deep network, you take your inputs, the first layers process, low-level features, and then as you move through this network, you get more and more abstract representations of the network. And these are now famous pictures. I think Google searched deep neural network, and you find something like this. I didn't cite where I got this picture from. I did that intentionally because actually everyone steals these pictures. They steal them from my office mate in grad school. So I remember when Hong Lak Lee was building these pictures, because I was sitting next to him in my office in grad school, and they've become now famous, these notions of, the first thing's finding edges, the next one's finding parts of objects, and the last one's finding whole faces and things like this. So this is obviously a true understanding of depth, right? This does, things like this approximately, we do observe them in deep networks, but I want to at least think about a slightly different way of thinking about depth. And the fact that it will work, these models I'll talk about will work as well, at least on some tasks, as these sort of more traditional hierarchical ways of thinking about things, I think says something kind of important about how we build and think about deep networks. So what does this talk about? This talk is about how we can I'm going to show you how we can take a deep network, almost any deep network, not quite all of them, but almost any deep network, and replace it with an equivalent version that is one layer deep. It'll have the same number of parameters. We're not doing exponential blow up or anything like that. It'll have the same number of parameters, and it'll have the same representational capacity, exactly, actually, but it'll be one layer deep. Now, there's obviously a trick here. The trick is we have to move from our notion of layers as being just feed-forward computation to what we call implicit layers. They're layers defined as the solution to some nonlinear equation. And when we do this, it's sort of a very easy way to get this result here. But the actual interesting thing is when you take this idea and then throw away depth and just think about deep networks as trying to solve nonlinear equations, at least in some domains, and we're going to look at sequence modeling in particular, they work basically just as well. So you can get just as good empirical performance, even on some large-scale language modeling tasks, as you do with these very complex, deeper networks. So that's the agenda. And here's how I'm going to do it. I'm first going to talk about generally implicit layers in deep learning. What I mean by this, and more importantly, sort of how these work, what else we've used them for, and how you treat them as layers in a deep network. Then I'm going to talk about our particular instantiation of this, called a deep equilibrium model. And this is sort of this specialization of this notion that gets at this notion of replacing deep networks with something a little different, even though we call it a deep model still because shallow equilibrium network doesn't sound quite as good. And then I'll finally talk about some results. And in fact, this is probably the most important part in a lot of senses. I'll talk about results showing that when you use these things, so sort of throw away our traditional notion of depth and just use these what we call these equilibrium models, we actually end up getting very good performance on some language modeling tasks while also having things like better memory consumption and things like this, because you don't have to maintain whole depth anymore. Yeah, Zach had a question.
I mean, just at the highest level.
Yes.
Be situated. Just what's the restriction? Because like otherwise, like, we represent any nonlinear function. Of course, we don't need depth because we could just go straight to our output.
Yeah, just call like the whole thing one layer, right? Yeah. So there's one nonlinearity. There's going to be one sort of nonlinearity applied after linear units, but with this implicit function form. So I'll get to that in a second. Yeah, it's not going to be that cheating. It's still cheating, but it's not just like saying, oh, we'll call a whole network just one layer now. So it's not quite that much cheating. Okay, so let me talk about implicit layers first. And this is actually something that comes up in a lot of contexts. It comes up actually mainly in the context which was sort of the original topic for my talk, which was embedding constraints into deep networks. And we've used this sort of formulation in a lot of different ways within different aspects of deep learning. So the idea, though, is very simple. The idea is, now we're back to the normal deep setting. So we say we have some input x, a bunch of hidden layers, and some output y. A normal deep layer, or a normal layer in this network, so what I typically call it an explicit layer. It means we have an explicit form of how you compute the next output given the input to that layer. All I'm sort of arguing for here, or all I will sort of advocate for, is replacing this notion with an implicit layer. And this says instead of representing a layer as a computation about how you actually compute the output, just represent a layer kind of as a root finding procedure. So we have some nonlinear function, and we want to form our output such that f of our input layer and the output equals 0, where this is some nonlinear function here. And it turns out this representation is very, very powerful. What you can do with this, as you might imagine, because we all work with root finding and then solving an equation like this is obviously a very powerful paradigm if you can do it, when you can do it. This type of layer has both a lot of applications and it sort of opens up, I think, a new possibilities, new ways of looking at what we mean by a layer in a deep network. So let me give a few examples actually of past work we've used that uses this kind of layer to, I think, nice effect in deep networks. Yeah, Matthias.
You're going to list some prior work?
Yeah, I'll list some prior work first. This actually was the main topic we were sort of dealing with before, but I decided to switch a little bit. But let's spend a little time talking about what good is this, right? What does it actually buy you to think about implicit layers? So the first one I'm going to bring up is some work we did a couple of years ago with my student Brenda. Yeah, another question?
All right. So writing it in this implicit way is the way the control theory community developed backprop in the 70s.
Yeah, absolutely. So so all this goes back decades, if not centuries, about how you actually backprop these things, and then it's really classical stuff. There's nothing new mathematically here. It's more of a different way of sort of thinking about it. But yeah, I'll get to that in a second. Okay, so one of the first applications we had of this was an architecture we called the OpNet layer. So OpNet was basically a layer in a network where the layer itself solves a quadratic program. What I mean by that is the output of this layer is the argmin over some variable z of a QP where the QP itself is set up, parameterized by the previous layer. That can be very arbitrary, right? So our Q matrix, our cost term here, and our quadratic and linear cost terms can depend actually arbitrarily on the parameters, the inputs to the layer zi. The constraints, the equalities and inequalities can also depend arbitrarily on the parameters zi, the inputs to the network. And you can have, of course, parameters of the layer too. Like some of these can be fixed, some of them can be just parameters of the network. But this is essentially a layer in a network now. We think about the layer's output as being the solution, not the value, but the actual argmin, the solution to this optimization problem. And in that paper, we showed that actually you can do a lot of stuff with this. You can represent a lot of functions more efficiently, more compactly than you can with most networks. And you can also solve some sort of cool problems that deal with things like denoising images or solving little puzzle games and stuff like this. And now the important point from this perspective of this implicit functions, though, is how we go about representing this layer. Because it seems hard. I mean, how do you differentiate through an argument? It's actually not hard, but it seems hard upon first glance. And the way you do it is you represent exactly this network as an implicit layer. this layer as an implicit layer. So the way we know we find a solution to an optimization problem is through the KKT conditions, right? Those specify, for a convex problem, at least as long as you make sure this is convex here, they specify sort of conditions that will guarantee optimality of this program. So you think of the solution, really the solution both of the next outputs layer as well as the dual variables. Those could also be outputs if you wanted them to be. You have to find a zi plus 1, a lambda, and a nu such that they satisfy these equations. These are the optimality conditions. The details here aren't important. These are standard KKT equations. They actually also have to satisfy feasibility here, but these are the ones that matter for differentiation. You have to find ones that satisfy these equations. These are not linear equations. They're nonlinear because of this complementarity condition here, so they're not easy to solve, but they are solvable. There's been, of course, a ton of work on doing this. And the key point here, though, is that this layer, this seemingly complex layer, is easily parameterized in terms of this implicit function, solving this implicit equation. All right, now I want to give a few more examples, just one more example of this actually. I'm not going to have any of the math here because it's a little bit more complex, but it's the exact same idea. We had a paper this year earlier at ICML on doing a similar thing for solving, I guess, a smooth approximation to SAT problems within a network. So you can also formulate an optimization variant of SAT called the max SAT problem, and you can form a semi-definite relaxation of that problem. There's a lot of steps here, actually, because you have to form a fast solver for that semi-definite problem. But basically, a very similar set of techniques hold, and you can characterize solutions to this problem, this sort of satisfiability problem, as those solutions that satisfy a particular, in this case, just a set of equality conditions. Nonlinear equalities, but just some set of equality conditions. And this basically gives us our implicit form of this layer. Now I'm not going to get into the details here. We can do some very cool things with this, though. Like we can learn to solve Sudoku problems just from data. So given a bunch of Sudoku problems, actually not even that many, because it sort of constrains the system to learn logical representations, we're able to do things like give it inputs and outputs to this form, and it eventually will learn the rules of Sudoku and can play Sudoku on new problems, even though it's never been told the rules of Sudoku kind of in any formal way. So again, not getting too much of this, because we've done a lot of work in this area. We've also worked in things like physics, differentiable physics simulations. We've worked at game solving, so finding Nash equilibrium of games. All these things can be represented in this form of implicit layers. So just finding some next output of the layer that satisfies some nonlinear function. And the question, of course, that comes up, which is pretty easy to answer, is how do we incorporate layers like this into a traditional deep network? What this really involves is how do we compute the relative Jacobians, or actually more specifically, how do we backprop through one of these implicit layers? Well, fortunately, this is, again, as Matthias was suggesting, this is a really old technique. It just goes by the name of implicit differentiation. It's at least decades, if not centuries old. It's decades old in this instantiation, centuries. But you apply something called the implicit function theorem. And the idea is, we know that at our solution, we have this equation holding, right? We have f of zi, our previous layer, and our next layer. I'm going to write this as a function of zi, because of course our solution is actually a function of the input layer. We know this holds, and this function is 0 at the optimum. And now we just differentiate this thing. So we differentiate with respect to, say, our input, though we could do the same thing, differentiate with respect to the parameters of this thing. We apply the chain rule. So the first term, we take this first term here, we get this Jacobian, we take the second term here. Both these two terms, the zi's are treated as constant, so it's just the Jacobians at the actual solution. And then this term here, this last one, also just to clarify, those two things are things you know. Those are just standard automatic differentiation terms. This last one is the unknown, it's what we want to compute. And so you just now have a linear system that specifies your solution. And this is just, again, implicit differentiation that goes back decades, if not centuries, actually. Yeah, question?
Does zi plus 1 have to be unique for each zi?
Sorry, what was that?
Zi plus 1 have to be unique for...
Right. So there are a lot of questions like that. I'm going to assume here that they are unique for the most part. If they're not unique, then this Jacobian will not be invertible. There are things you can do to make it invertible when it's not quite invertible, like a little bit of regularization, right? So just minimize a little hinge term, a little hinge term, or sorry, not hinge, a little L2 term on it in addition to make it unique. That's usually not that big a deal. The bigger question actually is how you solve this thing, because they typically are pretty. I mean, we're solving an inverse now to do backprop instead of just computing a matrix transpose, and that can be hard. But the nice thing about this is that it's actually typically easier to do this. Just solving this linear system essentially is usually easier than finding the root to begin with. So if you can find a way to solve this implicit layer to begin with, it usually pretty much gives you an indirect method to solve this thing as well. And then we'll end up exploiting that. We actually exploit that in all the previous works we have. You use your solve solution technique here to essentially give you an equivalent one to solve the backprop equation as well. And there's actually a very general form of that where you can derive that formally, that a solution technique here will give you an iterative method to solve the reverse, but we typically do it by hand still. We're not sort of doing it quite in the fully automatic differentiation mode yet. Okay, so there's one important takeaway that I want to make after all of this, though. And that is, and this is what we exploit in all these past works, is that to differentiate through an implicit layer, we are not advocating unrolling the solution procedure and then treating that as a computation graph and backpropping through that. That's expensive, especially memory expensive, right? Because it could take a lot of time and a lot of computations to find that root of that equation. We're not advocating for that. What we are instead advocating for is finding that solution using any technique you want and then analytically differentiating through it with the implicit function theorem, which typically is much, much more memory efficient and better in a lot of ways. Yes, question?
I just wanted to give more examples on this. So for example, using sparse coding to go from one layer to another.
Yeah.
And that this implicit differentiation has also been used.
Yeah, absolutely. So I think Julien Maral had some work on that, but then it's also been going on much further than that. I think how to differentiate through optimization problems, how to differentiate through these implicit functions. Yeah, it's a great technique, not actually used all that much still, but known for a very long time. Yeah, so that's
How is it related to? There was a last NIPS, one of the winning papers. The award-winning papers was about differential.
The ODE-net paper, yeah. So actually, that is very related, not very related, but it's definitely related to actually what I'm talking about next. But that actually is implicit layer. So you can think of an ODE as a solution, a set of trajectory that satisfies some equation, and the adjoint is exactly the backward pass operator. And adjoints, have been used for decades in ODEs, so they're very well understood. Yeah. That's also an implicit layer, though. Would be the way I would characterize it. Yeah.
I think the paper by the quote lister just unroll the iteration speed.
Yeah. So I would not advocate for unrolling iteration schemes. I think that's actually a bad thing to do, because you have to maintain your intermediate products through that whole unrolled scheme, and that kind of defeats a lot of the purpose of this nice stuff. And in fact, one of the big benefits we're going to highlight from this is the memory efficiency. Is that you don't have to worry about backpropping through multiple layers, maintaining multiple things. So that's sort of the benefit here in some sense, but they both do have some advantages too. I think it's just better to differentiate analytically through these things when you can do it. Okay, so having said that, let me now propose a particular class of implicit layers that I think raises questions about what we mean by depth in networks in interesting ways. So I think we haven't quite figured out all the implications of this yet, but I think it's a cool idea, and I'm excited to see what people think about it. Okay, so here's our agenda. So what I'm going to do is I'm going to show how we can represent pretty much, not quite any, but almost any deep network with a single hidden layer network, with the catch being that this hidden layer needs to be an implicit layer. It's actually a very trivial reduction here. It's not hard at all. You could maybe even imagine how it's going to work. But it's still saying something interesting about it. Because once we do it, we're going to say, let's forego, because we can do this now, let's forego any sort of notion about depth as being some hierarchy of different things. Let's talk about depth as just computing the equilibrium point of some function, of some dynamical system. That's what we're going to think of as depth. And those equilibrium points end up being really good feature representations for our input, even though it's just one layer kind of repeatedly applied, or even a root found for one layer. It's, again, similar but distinct from this neural ODE idea, where it's sort of more about a trajectory and then differentiating through this continuous time thing. This is a much more discrete thing, but definitely related.
Same number of nodes?
Was that?
Same number of nodes?
The reduction in general will not have the same number of nodes, no. But the big empirical result that I will show, which is the next section, is that if you keep the number, not quite the number of nodes, but the number of parameters constant from this network to this network, it works basically just as well, at least on the tasks that we do. And we're doing some real large-scale tasks here, some language modeling tasks that are pretty large-scale. And this works plenty well. OK, so let me go through what I mean by this. So again, traditional layers here. So first of all, we're going to consider a specific class of network to do this reduction. And it's going to be called what we call a weight-tied input-injected network. And we actually need both those things, or it doesn't quite work. So what do I mean by that? Well, normal networks, you have your input. You apply a bunch of different layers to get your output. What we're going to do, we're going to consider the following network. A network where you have your input, and at every layer, at least after the first one, you apply the same matrix W. So it's always the same matrix you're applying. This is what's going to cause it to be an equilibrium point, really. And you always also re-inject your input into that layer. So instead of just like a ReLU of a linear function here, you have, say, a ReLU of some fixed matrix applied to your input plus some linear term applied to the previous layer plus some linear term applied to your input plus a bias term. So we're going to consider these types of networks. Now, the first thing you might say is that this seems like a pretty big restriction on the class of networks. But it actually isn't, at least not fundamentally, because it's easy to reduce any network like this to a weight-tied network. And the idea there is you just can do it by just expanding your depth to capture both layers. So say I have some network like this, some iteration like this, where I have Z2 equals some function of Z1, Z3 equals some function of Z2. I can capture all of this by just embedding it in a single network where I sort of have a concatenation of all my hidden vectors there. I apply the same matrix each time, and I get the output there. This is equivalent to these two. It's cheating, to be clear. It's totally an easy reduction. It's not hard at all. Also key is this does not become a single layer network, right? You have to apply this thing twice to actually make it equivalent to this. But if you apply this same weight-tied network, you get the same thing. Now, we are not going to do this in practice. We're not going to. This requires a very specific sparsity pattern for this matrix here. We're not going to do that. What we're going to do is we're going to instead just match parameter counts between, shrink this down to match parameter counts between this and the original thing, and it will work just as well. So we will ignore any of this sort of structured version of the equivalence, but just I'm going to sort of making the argument here that the things are in fact equivalent. So we can reduce any normal feed-forward network to a weight-tied network. Yeah?
So are you learning both U and W?
Yeah, we'll learn U and W will both be parameters here. I'm omitting U here, but yes, U and W are both going to be parameters. They're just the parameters of this network. Yeah. OK. So theoretically, no is not a big restriction because they're equivalent. And empirically, no, too. It turns out you take basically any network, and you repeatedly apply just a bigger weight-tied version of that network, and they work about the same. Now, if you just do this sort of naively and just apply the bigger weight-tied network repeatedly, it's kind of slower, so you actually don't really gain very much. And you're still sort of memory intensive because you have to backprop the whole thing. So it's not a great thing to do naively, but it's still a reasonable strategy. We actually had a paper on this that talked about sort of an equivalence between RNNs and convolutional networks based upon this idea of unrolling weight-tied networks. So unrolling weight-tied in depth, where every layer of depth has the same weights applied to it. And this is one work we had at ICLR this year. Yes?
So regarding the theoretically common no, I mean the other issue of your construction is you're feeding in the Z2, the output.
No, this can be 0. Make these 0 at first. I mean, they don't matter, right? Like they'll disappear in this first one, so it doesn't matter. Make these 0 when you start. Oh, the question was, it looks like you're feeding in Z2 and Z3. And I would say no. So these are 0 initially. So your initial vector you feed in is Z1, 0, 0. After next time, it'll be 0, Z2, 0. And the next time, it'll be 0, 0, Z3. You can also keep them around if you want. You can make the final thing Z1, Z2, Z3 by just propagating terms forward. But it's easy to keep. It's easy.
Okay, now doing these repeated applications.
Yes. Yeah.
How
Yes.
is performance measured?
We're going to talk about performance in a second. I'll get to that when we talk about the actual performance of these things, yeah.
That's to here. The first line is Z1 equal to 0. Sigma and everything there.
Yeah, so the first line would, if you initialize your vector state with Z1 equals to Z1, I mean, this is sort of just, hopefully you can see how this works, right? You make Z1 equal to whatever input you want in that left-hand side. You make the other two terms 0. You apply it once, and you will get Z2 out in the thing. You apply it again, you will get 0, 0, Z3 in your vector there. So you can, I mean, and you can do whatever you want. You can maintain Z1 if you want to, also just adding like a residual term. But that doesn't really matter. The point is, this is a trivial reduction if you want to do it this way. And the only point I'm making is that we don't actually lose that much by this weight tying structure. OK, so now, hopefully, the idea is becoming kind of obvious here. The idea is we're talking about deep networks. That means the word sort of deep in quotes here as just repeated applications of the same function, where this is a function of both the previous layer and the input. And that's our deep network. So, in practice, and we'll discuss this a bit more shortly, whenever you do this with an actual deep network and apply them repeatedly, this process will converge to some equilibrium point. And so we can think of, in some sense, the infinite depth neural network as just computing an equilibrium point of this dynamical system. That's what it's doing in depth. Now, there's a lot of assumptions there. You know, is it stable? Is it going to converge, et cetera? I'll talk about those more in a second. We don't have too many strong results there, but it's actually, in practice, the answer is yes, they always converge. Because if they didn't converge, it'd be a really bad deep network to begin with. Because 100 layers deep, if it's not stable, it's already going to blow up. So we've already designed stable deep networks in this sense. Now, our model, the deep equilibrium model, all we're going to do is we're just going to advocate to find this point directly, which of course is finding the root of this minus z star, right? So we're finding it's an implicit layer still. All we're advocating for is that instead of trying to find this in the naive way by just repeated application of our function, just use a root finding technique to find that directly. Whatever you want for root finding, use one. It's going to be faster than repeated application typically. Just find it with root finding methods. We use Broyden's method. You can use a lot of them. And then analytically differentiate using this implicit function theorem. And that's it for the deep equilibrium model. OK, so just to summarize here, summary. So now our task is nicer as deep learning architects because we only have to find a single layer. We don't have to worry about multiple layers, and all the connections. I mean, I know, especially in like vision tasks, it's going to be harder because we haven't worked in those much. We're talking about sequence modeling. It's a little easier here still. But you define a single layer, basically. And this is a simple version. You get a little bit more complex with like transformers and things like this. But this is sort of an approximation of what we have. And the forward pass, you just compute the equilibrium point, which I'm writing here just to emphasize the implicit nature of this, written here as a root to some nonlinear equation. And then the backward pass now is just, if we want to find derivatives with respect to any parameter here, we just apply that implicit function theorem, and what we get out is the following thing. That we can compute any gradient we want with respect to the loss by looking at the gradient of the loss with respect to our output of this layer times this, which is the Jacobian of that term, times whatever derivatives we want there. And that's just the application of that rule you saw before. All right, so that's it. Yeah.
So I have a question regarding these models. So if I take f to be something reasonable, like a single Residual layer, or maybe even a linear layer,
Yep.
Can you specify some interesting class of predictors that these models can actually represent?
Yeah. So I mean, right. So I think yes. If you think of it as a ReLU, then by the construction before, you can in theory represent any deep ReLU network because you could always have this weird chained structure in your W matrix that sort of propagates things forward and then ends after a certain amount of time. You could always sort of replicate if you wanted to by a quadratic blowup in parameter count. You could replicate, actually not really because you have a lot of zeros, but if you didn't constrain it that way, you could always replicate an existing deep architecture. Now,
Talking about
I think
infinite depth here, so.
yes. So you could always sort of say that after a certain time you don't use that last element in the next predicting the next element. So even though it's infinite depth, it actually converges after k iterations, and you have exactly the previous deep network. Now, to be clear, we don't do any of that in practice. What we just do is have a normal, arbitrary matrices for W and U, and they converge to something kind of cool. To be honest, we haven't really studied like what's the real class of functions it's representing here beyond that too much. So I think it'd be really interesting to think about from a more fundamental perspective, what's the real representational power of this thing? And the short answer is, we haven't done much more than just say we can represent other things kind of easily.
So in terms of implementations,
yes.
The gradients can never use the auto differentiation. You have to code the gradient.
Right. So the question was about we can't use auto differentiation, right? Because you have to solve this equation exactly, and you have to solve this with some Broyden method too. So yes, you have to implement a wrapper that sort of says, okay, for whatever Jacobian your inner layer has, here's how we're going to implement a solver to compute our Jacobian. So in PyTorch we have a meta model where you plug in your layer here, and it will compute through its auto differentiation to compute what it knows about. It will compute this thing using Broyden's method for the forward and backward passes. But you only do that once, right? And then you're good after that. All right. So a few frequently asked questions. The first thing people always say is, okay, great, you have a new, more powerful representation. We're deep learning people. Why don't we just stack those together and get even more power? And the answer, which I think is very cool here, is that it doesn't matter. In this formulation, there's no advantage representationally to stacking equilibrium models together. Because if you have sort of two things like this, so these are both sort of equilibrium computations here, right? This first finds an equilibrium point at this first function f1, then equilibrium point at the second function f2. Again, really trivial statement here. This thing is just the same as an equilibrium point of one function. You just stack two functions together. This is now a function of both these variables and the input x. So it's just an equilibrium point of a single bigger function. This is what's really nice about this sort of implicit layers, is when you have implicit layers, there's no representational advantage, you don't add representational power fundamentally by stacking them. One layer, this is what I had in the beginning, right? One layer is really all you need. You don't need more. Now, for optimization reasons or something like that, maybe you do want them. Maybe you want to separate some sort of notion of modules, but you don't need them. You can do without them. Number two, how do we compute forward? I think I already mentioned this. We use Broyden's method. The cool thing, though, is this is sort of our first. It's a quasi-Newton method. It seems reasonable. All the time that this takes, all the runtime that we're adding here in some sense, is all just about finding a root to a single equation now. So if you know the structure of your problem in a way that lets you exploit that to find a root more quickly, you can actually solve these things potentially much faster, though we haven't exploited that too much yet. And we use it for both the forward and backward pass, and I think there's lots of hyperparameter optimization to be done here to make these things much faster. Yeah?
What sort of Fs can you have?
Just think of F right now as being this, but what we're actually going to do is we're going to make F like an LSTM cell, or we're going to make F like a transformer block. That's what we actually do, because you can't compete with the state-of-the-art with just a ReLU. So what we actually do is we make F essentially a single block of like a transformer. And that's actually how we're going to get results that are competitive with the state-of-the-art.
The F can still be the convolution network?
Oh, yeah. It can be anything. Any operator you can code in PyTorch that can be your F, including a few stacks of layers if you want to have like a transformer with self-attention and then a linear layer and then a layer norm. You can do all that, yeah. So it's not quite one layer, I guess, there, but I'm cheating like Zach has maybe called me out for a little bit. But it's still kind of one layer. Right?
You mean you stack layers into the F? So
yeah, you can stack a few. So like what a transformer is, right? A transformer is like the self-attention layer followed by a single feed-forward layer followed by a layer norm, and there's some other layer norms maybe intermediately too. You can do all that, and so that becomes our F, for example, for the real state-of-the-art models, because you can't just do that much with a single ReLU. You can't get there. But it's only one transformer layer. Then after you're done with that, after you have your single block, your single cell, you're good to go. Which is kind of actually the mode people think about. Like they think about doing like architecture search at like the cell level. So you have like a cell, but then you repeat that in this infinitely unrolled weight-tied sense. Okay, do they exist, these equilibrium points? Good question. Zero theory about it, because they may not. They're nonlinear functions, arbitrary nonlinear functions. They're weird functions that haven't been studied. We don't know if self-attention followed by layer norm is really a contraction in all cases or not. But in practice, yes, of course they converge, because if they didn't converge, there's no way a 18-layer transformer would converge ever. It would already blow up after 18 layers. So the reality is these things do exist, and in practice, we can find them. A lot more to be analyzed there and sort of seen there, but this is where we have so far. What's the trade-off between this? Is it really faster? I mean, you would think maybe ideally, okay, maybe this is faster than a deep network, right? Because we're just finding one layer. The answer is that right now it's not faster. It's about 2 to 3 times slower at training and about two times slower at inference time. The reason for that is that finding a root is still a reasonably intensive task, and even with a method like a quasi-Newton method, it requires a few function iterations, and so typically it requires to find an actual root, which is more than what currently networks are doing, right? They're just doing 18 layers or something like that. To find a real root, you have to iterate these things for a few times, and so it's a little bit slower to train. Now it's much more memory efficient though, because you only have to maintain the memory of one block. Because you're not unrolling computation, you're just doing analytic differentiation, so you can just have that one block. So it's more memory efficient, less, a little bit slower, but I think this actually can be brought down a lot, and we're actually more in like the 1.5 to 2 now, if we just sort of cut down the number of Breuil iterations, and it still works fine. We still get convergence. Maybe not exactly, but it's good enough, and it still works just fine. So there are trade-offs involved, but conceptually, it's simple, right? It's just saying find one root, then go from there. Okay, so now let me actually say the main thing, which is short, but actually isn't something the actual punchline of this. Yes, question?
So, if you go back to your previous slide,
yeah.
Can you be specific about what you mean by equilibrium point?
Right, so what I mean by equilibrium point is this. And sorry if I didn't actually say that more formally before. What I mean by equilibrium point is you have a point where you have a value for a hidden layer, such that when I apply my function to that value and the input, I get the same value out. Now, because I'm applying the same function layer after layer in depth, if I have this point, that is equivalent to kind of the infinite depth version of this network. There's a point where the value does not change anymore, and hence it has converged to its equilibrium.
But that's actually a function because it depends on x.
Oh, absolutely, yeah. I mean, you have to solve this equation to find that point. It is a function of x. I mean, right, so if you ignore input injection, this is actually a good question. Like, well, what if you leave out input injection? Why do we need that? Well, if you do that, then this function doesn't depend on the input anymore, which seems a pretty bad idea for a deep model. So you actually need your input injection to actually have some dependence on your input, which is a good idea if our networks depend on the input we feed to them. Yeah?
So if I give you a deep network with tie weights,
yep.
How do I find the function, the implicit function f?
Oh.
And the dimension of the hidden layer z, and
with tied weights? Because if you have tied weights, then this is just already in that form. A weight-tied network is already in the form of a function. I mean, this is how networks are represented, right? It's the output of a layer is the output of a layer is some function applied to the input of that layer, and in our case, and the x. So you already have, this is the function f here. Yes.
So your f should be contracted, right?
Yeah, so f again, it should not only exist in equilibrium, it should be a stable equilibrium, meaning that points will converge to that equilibrium. And again, no reason why that should happen in theory, but we can't prove it happens, but in reality, networks are really bad if it doesn't happen already, and so they do happen in practice. It's contractive and it converges to I mean, again, is it unique? No reason why it should be. It's nonlinear. In practice, it seems to be. We haven't been able to find cases where it doesn't seem to be unique. Yeah.
So you've checked whether the root that you find via like Breuil's method is the same?
It's the same one, yes. And it is, yeah. Yeah.
Just a quick comment. People were curious about counterexamples of functions that do not have equilibria. Many of the worst case constructions are not equilibria. So digit extraction and all the depth separations, they do not have equilibrium points.
Yeah, so there's plenty of functions that are not contractive in this regard, right? It's a nonlinear function. Of course it can be non-contractive. Again, real networks typically are. It's the same, yeah.
Do you need contraction though? I mean, if you're using like a...
Yeah, great question. Okay, so excellent question. So the question is, why does it even be contractive? I mean, we're finding roots. That's good enough. We can make it contractive sort of with the Breuil iteration. So yes, you don't actually need it, but in practice you just simply have it anyway, and so it's good enough. Now, what actually is interesting is that, and this is maybe we'll talk about this, we can talk about this more offline. What's interesting is that they're sort of like critically stable, these things, and as you train them more, they get closer and closer to being almost unstable. And so these methods typically are able to find kind of nicer routes than that would take a very, very long number of iterations to actually converge to if you just did the unrolling of the forward iteration. But maybe we'll talk about that more offline. Or maybe I wasn't quite answering your question, but hopefully I was getting at the main point. Yeah.
Do you need to solve the equilibrium very accurately?
Right. Okay. Another great question. The question was, do you have to solve the equilibrium accurately? The answer is no. You can, I mean, we did it first, which is why we have that slower thing. We've sped it up a little bit by requiring like 10 to the negative 1, so 0.1 residual is required. We stop then. This is a very common thing in indirect methods, right? You just stop when you're close enough. And I don't have it here, but in the paper we have a plot of, and again, it's not quite out yet, but it'll be out in a few days. We have a plot of the solution you converge to versus stopping criteria, and it's basically flat at the same level until you get to like 0.1, and then of course it shoots up because if you have, if you're not converging at all, then you're not learning anything. But you can go very, very loose with that convergence criteria in practice. Yeah.
Another question. What if you were to apply optimization beforehand?
What if you were what do you mean by that?
Like pruning or something.
Of the network itself? I think it's an orthogonal issue. I mean, you can prune the network. For most reasonable prunings, it will still be stable. You're just making weights more towards 0. That isn't going to probably make them unstable. But I think pruning beforehand is kind of strange. So maybe like pruning afterwards, something like that. I mean,
then you're pruning the single layer. I mean, like.
I think it works fine. I think they're orthogonal things. I suppose it will work. All right, let me get to the final bit. But I guess you already all trust the results are going to be good. So maybe I'll say those for a second. But yeah, one more question.
Yeah. So basically, you're saying that the representational power of these models is the same as an infinite depth weight tied input injected.
Correct. Yes. And those are themselves sort of good representatives, both in practice and in theory.
Because I know that if you don't have weight tying,
yeah.
You can get a universal approximation theorem with like a finite width.
Yeah.
Sufficiently deep, you can represent any like Sobolev space function.
Right.
But I'm not aware.
Well, for any finite depth, you can play that trick of just encoding it along these sort of like with this like shift operator. So for any finite depth, you can get the same thing with an infinitely deep model also. Okay, so now the part that I guess I've said this already, so everyone's going to be convinced already by this, but we're going to apply this to the task of sequence modeling. So sequence modeling basically is the problem of given a sequence of inputs x1 to xt, predict some set of outputs of the same size in our case here, y1 through yt, where the constraint is that these have to be causal predictions. So your prediction at time t can only depend on x up to that point. And that causal structure is basically embedded in the structure, in the allowed relationships of these hidden layers. There are lots of common architectures for this. There's, of course, recurrent networks, convolutional networks. Recently, transformers have sort of taken the mantle as the go-to model for a lot of sequence modeling tasks. And of course, there are lots of applications, time series prediction, language modeling, lots of things. What we're going to do, in particular for these results, is we're going to build 2 versions of these DECs. Deep equilibrium DEC, we call it, right? I don't know if I've ever used that acronym before, but we're going to use 2 DECs for sequence modeling. And the reality is you can easily extend the methods that we described previously, sort of just rote by rote application, to whatever kind of module you want. So we create 2 modules here. We have a DEC TrellisNet. TrellisNet was our previous work on kind of unifying the ideas of RNNs and temporal convolutional networks together. And we have a version on a transformer. So transformers are, of course, this self-attention network that has kind of taken over the world of, say, language modeling and also, for both predictive models as well as sort of these encoding, these sort of word embedding models. And we're going to have versions of each of these. And what I mean by that is we sort of take the single layer of one of these networks. And by layer here, I do mean maybe a few layers, because again, like a TrellisNet will have LSTM-like gates. Transformers will have a self-attention layer followed by a linear layer, followed by a nonlinear operator, followed by a linear layer, followed by a layer norm, or things like this. And so we just embed that as the unit layer in these deep networks and consider an infinitely unrolled version of that network. Now, we are not going to play any of those tricks I said before about actually stacking the weights in a way that makes them equivalent to a deep network. We're just going to let the weights be arbitrary, and we're going to make them a little bit bigger such that the total parameter count is equal to the parameter count of the original model. That's how we're going to sort of match models here. So the first thing I'll mention is just a few small-scale benchmarks. This is sort of uninteresting, I suppose, but on sort of standard tasks like copy memory tasks, this is sort of like a standard tool for evaluating, was for a long time at least, for evaluating recurrent networks. They work fine. A little bit better, but this difference here is meaningless. It's basically just, this task is you have sort of a sequence, you have a lot of zeros, you have to then predict that sequence at the end again, and it works fine for that. On things like small-scale language modeling, like Pentree Bank, here we're comparing just to TrellisNet. Transformers, this data set's too small, unfortunately. It's like the MNIST of language modeling at this point. So transformers actually are too powerful, I think, for this data set still. But essentially, so what I'm showing here is a TrellisNet structure on it, which gets not state of the art, but certainly competitive results without a lot of hacks for this. And we basically recover the same performance as a TrellisNet, a 60-layer TrellisNet on this. The difference being that this one gets the same perplexity performance, but it uses about 8 times as much memory, because in a 60-layer TrellisNet, you have to store all those 60 layers and the hidden activations as you go. Whereas for a deck, you have to just store your one layer. Now there are a little bit, it isn't quite, there's a constant on this because you have to also run like your Broyden method and stuff like this, but it's essentially O of 1. It's not going to grow with more depth. In fact, this is infinite depth already, so you're good. Yeah, question?
There are techniques in like...
Yeah, like gradient checkpointing and stuff like that, yeah. So we compare to all those. It works better, obviously. So the difference with gradient checkpointing is root depth, right? I mean, you can have other schemes. You can have other schemes that do it differently, but then you have more compute if it's log depth, like a lot more compute if it's log depth, right?
It's still like, I think it's like a factor of like...
it should be a factor of log, of log n, right? Yeah. So usually, yes. So we compare it to the gradient checkpointing. It works better than this. It's more marginal than memory, like computation. It's sort of, it's on a Pareto curve with the other ones. A little bit better in some cases, a little bit worse in other cases. But again, like fundamentally here, it's still an O of 1 technique, right? And so I think that's the idea here, is a little bit more fundamental than that. I think as a practical technique, it's on the border right now, but we have to see, is it going to really compete against gradient checkpointing in terms of all these things? But right now it is better, to be clear, what we tested against. It's just there are other parameters you can probably tune.
What does the speed here mean? The higher the faster?
Higher is slower. So inference speed is the baseline is TrellisNet, and we're about 1.9 times that, because it's to run Broyden iterations for longer, because we're actually converging to a fixed point as opposed to not. Okay, let me show the final one now. This is actually the last slide I have, because we're out of time. But I'm going to talk about now Wikitext 103, which is a reasonable size data set. Not the biggest one, but it's a reasonable size text modeling data set. And we're going to compare against mainly Transformer XL models, which are a state-of-the-art language modeling technique. They're really good for sort of predictive language models, which is a transformer technique that stores some history in its update equations. Okay, so let me just go through these. And you'll see a common pattern here. So on small with 5 million parameters, they get similar performance, the DEC transformer versus the Transformer XL, again, with less memory for the DEC. For TrellisNet, with a 70-layer one, again, similar performance here, a little bit better here, but similar performance, and much less memory consumption. Transformer medium, similar stories. We actually do a little bit worse here, which I'm sad about, but I think that's mainly, it just takes us a really long, this is a 4 GPU thing, it takes us a long time to run, and we don't have the resources that some certain places, the nameless have. But again, the story is similar in that Transformer XLs gets 24 perplexity on this data set, but using quite a bit more memory than this. And this sort of, these results hold kind of at a wide range, wide intermediate range. Now, I just want to highlight, we are not state of the art yet. So if you train transformers with 225 million parameters on several TPUs, like a TPU pod for a long time, you get better performance, and we can't match that yet. I think we still have a ways to go, both maybe conceptually in terms of making this work, but also just resource-wise, we don't have that. But for the biggest models we can actually run on GPUs, which are these two models here, we do in fact match the performance of state-of-the-art models while essentially having much less memory consumption and also less than gradient checkpointing in this case when we put it with gradient checkpointing. Actually, these aren't really deep enough to make a big difference because these are only like 12 layers deep. Matching performance with one layer being all you need. Okay, last question. This is, again, about a talk on emerging challenges and stuff. So the big question to me is, how should we think about depth in deep networks? We've always thought about, or not always, but I think a lot of us think about depth as kind of this hierarchy, this fixed level of this fixed layers of processing to go from one representation to another. And I think that's true to a certain extent. There's no question that this is true. But I think there needs to be more consideration of this viewpoint of these networks as dynamical systems. And what we're doing when we run these things feed forward, in a feed-forward fashion, is we're even if maybe we don't have weight tying, is we're getting towards some notion of an equilibrium point of some nonlinear dynamics. And I think that perspective on what deep networks are doing itself is quite valuable. I think it will have a lot of applications. Of course, a big question is what other domains will this work on? We haven't done much yet. But I think it opens up a lot of doors and questions about how we think about networks, and hopefully will lead to the next set of things that beat the transformer maybe in their next iteration. Thanks very much. All right, I know we're out of time, so maybe we'll just take questions offline and people can start.
Like one, if somebody's like...
Anyone dying to take the last question, keep everyone else from going to lunch more than I have?
Okay, well, let's thank everyone once.